Good morning, Thames. Unlike the previous problems, where we work in steady state, we will now solve the energy balance for an unsteady process. Let's solve a really important thermodynamics problem. We have a rigid tank that is being filled with air using a compressor. Initially, the tank contains air at a certain pressure and temperature. Then, over some time, more air flows into the tank, and at the same time, the compressor adds energy. At the end, the pressure inside the tank has increased, and we want to find two things: how much mass entered the tank and what the final temperature is. First, we clearly define our system. The system is the tank. Mass enters, but nothing leaves. Also, the tank is rigid, so the volume stays constant. And the process is adiabatic, so there is no heat transfer. Before writing the balance, we make one simplification. We neglect kinetic and potential energy. So we only consider internal energy in the tank and enthalpy carried by the incoming mass. Now we write the energy balance. The change of internal energy over time equals the energy entering with the mass plus the power supplied by the compressor. Then we integrate this over the filling time. This gives us that the change in internal energy between state 1 and state 2 equals the energy brought in by the added mass plus the total compressor energy. Now we interpret this. The left side describes how much energy is stored inside the tank. The first term on the right is the energy that comes with the incoming air. And the second term is the energy added by the compressor. Next, we use the ideal gas relations. Internal energy is proportional to mass and temperature. Enthalpy is also proportional to temperature. So, we can rewrite the entire energy balance in terms of mass and temperature. At this point, we also use the mass balance. Now, we compute the initial mass using the ideal gas law. Pressure times volume equals mass times the gas constant times temperature. From this, we calculate the initial mass inside the tank. Next, we calculate the total energy added by the compressor. Power times time gives us the energy input. Now comes the key step. The final mass depends on the final temperature through the ideal gas law. So, the mass and the temperature are coupled. This means we cannot solve them separately. We insert the expression for the final mass into the energy equation. Now we have one equation with one unknown, which is the final temperature. Solving this equation gives us the final temperature. Once we have that, we can compute the final mass using the ideal gas law again. Finally, we subtract the initial mass from the final mass to get the added mass. The key takeaway is that this is not just an energy problem and not just a mass problem. Both balances are coupled, and we have to solve them together. That's exactly what makes this type of problem so important.